Remember, you always have to assume something to get something out of economics, okay? And you don't want to do too many bad assumptions. You want to have assumptions that generate models that lead to good predictions. So we're almost done with the course. We've reached the most advanced model, I think. Everything else is downhill after this. It's basically looking at a search model in a general equilibrium, we call it a steady state. It's not really a general equilibrium like macroeconomists like to talk about it, because we don't look at consumption decision, we don't look at investment, but we look at a situation where the inflows and outflows are equal, and that there's no incentive for agents to change their behavior. But to do that, we really have to go to the firm side and describe what the firms are doing as well, because the firms are offering the jobs. And until now, we've only talked about the people who are accepting the jobs or not accepting the jobs. Okay, so the plan for today is to summarize last lecture in a somewhat detailed fashion. I'd like to go over that one formal problem, which is very interesting. It's the derivative of the value function at any wage in the acceptance range, which is interesting in itself, because it also gives you an opportunity to use integration by parts again. But it also shows you it's very important to understand what this formula means. And this reservation wage that emerges when you have on-the-job search actually means that the arrival rate of job offers while you're working actually affects your reservation wage, affects your willingness to take a job if you're unemployed. Kind of makes sense, it's intuitive. And you can show that the comparative static of increasing alpha 1, the arrival rate for the jobs when you already got a job, is actually increasing the reservation wage. All right, so we'll derive this model a little bit more. I'll show you this important result, and again, there are like several results in calculus. You should probably remember one is Leibniz rule. How do you differentiate an integral? How do you differentiate under the integration sign? And the answer is 3. There's 3 things you have to do. If you differentiate an integral with respect to some parameter, you have to worry about the effect on the integrand, what is being integrated, and the effect on the endpoints, if it's a definite integral. And that's what we're doing. We're differentiating definite integrals. So the logic is integration, area under the surface or under a curve. In this case, it's a curve. So if you change a parameter, what happens? The function changes, so the shape of the curve may change, and then something happens to the endpoints. And that's exactly what happens in the search model. Okay, so we'll get to that. That's number 3. And then I want to give you some intuition of what we're going to do for the rest of the hour. And then next week, is to think about this as sort of two functions chasing each other. One is the wage offer distribution, that's F. So if you get an offer, what is the distribution that you can expect? And of course, before the fact, you don't know what the wage is, but you're going to have an idea of what the distribution is. That comes from somewhere. And given that distribution, we have an implication of the search model for the distribution of observed wages. So F does not equal G, which we introduced last time. G is the distribution of wages we actually see in the data. So if this model is right, the distribution of offered wages does not equal the distribution of accepted wages. Okay, because there are some wages that are offered or turned down, and they will always be turned down in equilibrium. Okay, that's the idea. And then we're going to turn that idea on its head and say, okay, where does this offered wage come from? And there aren't many good theories about this. One of them is the Burdett-Mortensen model, which basically takes each employer as a wage poster. Posting means you post the wage. Instead of negotiating the wage, you post it, which is what we observe in the data. I mean, if you look at Germany, you go and look for a job and you get an interview and the guy says, I like you, and then he tells you how much he's going to pay you. It's not like he looks at your marginal product and looks at your labor supply curve. That's not the way this world works. Okay, that's important. And that's what makes this model very special. Okay, so it gives rise to a whole bunch of other stuff I'll talk about later, including theories of monopsony power, when firms actually have power to set wages. Okay, I find this one of the most exciting parts of labor economics right now, and there's a lot of interesting work being done. But to get there, we have to understand this other business. Okay, so we're going to repeat, until now we've thought about people's reservation wage conditional on a distribution of offered wages. We didn't tell you where F came from. Okay? The theory of search on the job with on-the-job arrivals implies something for the distribution of wages we actually observe. And then the next step would be to use that insight to use G, the generated distribution of observed wages, to make a theory about how the wages are actually offered to the workers that are working or unemployed. So there's going to be a mapping of F to G and a mapping from G to F. And these are functional equations. They're not equations in a variable, they're equations in a function. So it's like, it sounds fancy, but it's really not. And the way we're going to do it's very easy to solve. The brilliant aspect of this paper is that Burdett-Mortensen actually found a closed form for the distribution. Under certain assumptions, you can have very simple wage distributions coming out of a model. And again, where we're coming from, we talked about the diamond paradox. That's what's driving all this. The idea that is in a world where you have people all the same, how can you have a distribution of wages in the end? And Diamond, and he presented this paradox, and Burdett-Mortensen for the labor case showed that if you have enough friction in the model, you can actually generate this endogenously. So even though workers are identical in this model, they have the same productivity, they all have the same arrival rate when they're working and when they're unemployed, you can generate a distribution of wages that's sustainable. It doesn't collapse to a spike like Diamond criticized in '71. Okay, so that's the really neat. This is why I like this stuff a lot, because this is kind of, we observe people that look identical and they earn different wages. Okay, so you can get if you're a labor economist, you can turn on Stata and run regressions, try to explain wages of people, and if you're lucky, you can explain 40% of the distribution of wages with observables, if you're lucky, in a cross-section. Okay, so what does that tell you? Either there's a lot of noise, or there's a lot of unobservable stuff that we just can't see. It's just people's talents may be being compensated in the wage we observe, but we just can't see the talent. Right, that's the other alternative: human capital, skills, ability. And the other one is one we're doing today is just luck. So the guys who actually get high wages in this model are the ones that have managed to survive long enough in the firm and gotten accumulation of many raises. Okay, so these are two very interesting competing views of why wages rise with tenure, for example. Older people who've been on the job a long time tend to earn more than people who have not been around too long. And the question is, why is that? So these guys are pushing the envelope by writing down a model where everyone's the same ex ante, and they're ex post, they're only different because they were kind of lucky. Okay, so we're going to try to push that, and that's the last part. Any questions where we're going? So it's not too hard, but again, I tell you, the article to read, and if you want to survive this course, you got to read this article. Rogerson, Scheimer, and Wright, Journal of Economic Literature, 2005. Keep saying that, it's kind of important. Okay, so last time we derived the reservation wage when productivity can change. That was last Friday. So you imagine a worker just having random occurrences of improving or decreasing productivity for whatever reason, exogenous, but random. And then when that happens, the worker has to decide, well, do I stick on this in this job? I'm getting a wage cut, or wow, I got a wage raise. This is great. So knowing that structure of this setup, what is your reservation wage? It's different from the model where you just get laid off. Okay, so there's an incentive possibly to take a job if the offered wage is actually below the level of income and unemployment, because you're getting your foot in the door to move into a situation where you can actually get more offers on the job. And that's motivating the model today. So just to summarize that was the model of changing productivity. And this is just review and repeat. Should I shut that door? Probably should, huh? I mean, it's... Okay. So we're going to we stuck with the continuous frame model. And we looked at the reservation wages emerging when a worker has the indifference condition, and yet knowing that on the job things could change. The offered wage isn't forever, subject to a termination. So, in contrast, it can change. This actually is very relevant for Germany today. There's a lot of wage mobility upwards, but there's also wage mobility downward. We see this the so-called Kündigungs. This is what they call an Änderungsvertrag, when you're actually asked by your employer to accept a new contract, which may involve less favorable pay. In the old days, the unions would be up in arms about this. The unions don't have as much power as they used to. They can't fight back. And employers are trying to get away with this. So this is kind of what we would think of as an Änderungsvertrag, just put in the worker's face and saying, look, take it or leave it, and the worker can leave. That would be a case where the offered wage is below the reservation wage, and the other would be speaking to stay in it. Why would a firm do that? The firm that does that is a loser firm, because the firm's trying to, increase its profits on the back of the workers. That can lead to all sorts of other problems that we understand. Also, it's just not profit maximizing if the firm is competing in a competitive market and wants to make profits like the other guys. Why do you want to, chase your workers away? Because they would, under certain circumstances, go to other companies. It's kind of what today is going to go after. So we look at this asset valuation of the state of unemployment. The difference being that you have this risk of a wage change, which could be positive or negative depending on the situation. And we saw that if you have a conditional independence assumption, meaning you don't, the distribution of offers doesn't depend on your wage on the job, then we can actually solve for this model in a very simple way. Okay, and again, the logic of the whole course comes through again. We have a capital valuation of having the job, even subject to this possible risk of losing the wage you're currently earning. And the worker is not risk averse in this model, so you can add on risk aversion to these aspects without changing the underlying logic. But the firm's, the possibility that the worker might have a capital loss means that the valuation of a job at wage W is no longer as high as it used to be. Okay, so that's the. Now, we derived WR, and I'm going to show it to you again in a second. But most importantly, we jumped into this fourth motivation, this fourth modification of the model, which involves on-the-job search. Now just change your mindset. Think about a model in which we're still in the continuous time framework, but workers can actually get an improvement in their wage, okay, in that they get offers from outside the firm. Okay, so there's another arrival rate which describes just the arrivals, and we have to tell you where those wages are coming from, and we also have to think about what the worker can do. So the worker, under the assumptions of this model, will always turn down wages that are less than his current wage or her current wage. So in some sense, you can only go upwards in this model. Right? That's an important change. The assumption that Burdett-Mortensen made is that the wage distribution of existing wages is the source of wage offers. Okay, so it's like you're in a bathtub and you're getting offers from all over the wage distribution in this bathtub. Some people are working, and all the people who are working, those it's just sort of a mirror image of the structure of wages. That's the assumption of the Burdett-Mortensen model. You can change that, but it's not clear that it will sort of increase the intuition that you'll be getting from this very simple setup. Okay, so agents are risk neutral. They're always going to accept a job offer that from some other firm that's better than the one they have now, but they'll reject anything that's below. Okay, so conditional on arrival on the job, some workers will continue to work at the same wage, or they may go somewhere else and get a higher wage. Now the model is set up a little bit like Mortensen-Pissarides. It's one man, one firm, constant returns to scale. It doesn't matter whether you have 50 people in the firm or one person in the firm. So we have the scalability, and that's again for tractability, because big firms might have economies of scale. They might have a personnel department that could play the game differently than the small firms. So we're just going to wipe away those aspects for the time being. And the offers that you're getting from the outside, the so-called alpha 1, Poisson arrival rate is multiplying or is going to generate a wage that comes from this distribution. The CDF would be G. Okay? So as I said before, as I alluded to before, the key thing about this whole Burdett-Mortensen paper is that it generates this pair of functional equations that link two distributions. One is the one we can see, and the one that we, by construction, cannot see, because we don't have the data on people's job rejections. These are things, someone may ask, hey, you want a job? And you say no. So the data taker, the Bundesagentur für Arbeit, doesn't know about that. The Bundesagentur für Arbeit only knows about the G. Okay, so it's natural to ask, under what conditions can this job search model generate a G that looks like what we observe in the data? Okay, and under what conditions can we reverse engineer the offer distribution? What kind of model would generate an offer? And that's a harder question, because we're assuming one man, one firm in this setup, which means basically we have to have an assumption about the way firms behave. Are they competitive? Are they wage posters? When you're a wage poster, you're not really competitive, right? Even if you have jillions of other employers, and you say, okay, I'll give you €5 an hour, it's not very good. But if you say no, you got to go find another one. It may take some time. It's a model of friction. So you have to go back into the bathtub and swim around and find another job offer. And that's what generates this friction will potentially generate rather lousy wages at the bottom of the distribution, but those people are very likely to leave quickly. Okay, so the model's fascinating prediction is you have job turnover, which is related to the wage level. So we've observed a guy with a high wage. You can bet that person has been there a long time and will probably not leave. And if you observe someone at the low end, that person is very likely to leave quickly. Okay, and that employer will have a problem making a profit because that person needs that employer needs a worker to produce. So you see, the trade-off is that if you think of the workers, that the firm is posting a wage, then the firm is obviously going to consider, well, if I pay higher wages, it's going to cut into my profits, but I can retain the worker longer. If I cut the wages, if I play the bad employer role, then I have higher profits, but I can't keep my workers. So that trade-off is exactly what's at the heart of the Burdett-Mortensen setup. Okay? So we're going to derive that. We're going to derive that, and then I'm going to take this reverse engineering problem, like I said before. Now, to do this properly, I want to make you aware that we got pretty far last time, but we didn't get finished. Let me just refamiliarize you with the model as we dealt with it. Okay, so remember, you always have to assume something to get something out of economics. Okay, and you don't want to do too many bad assumptions. You want to have assumptions that generate models that lead to good predictions. And this model assumes two exogenous arrival rates. Okay, so one arrival rate is the arrival rate for the unemployed people in this model, and then you have the arrival rate for the employed workers. Okay, these could also be differentiated in many different ways. It increases the complexity of the model enormously. And again, we're looking for the insights of the relationship between job tenure, wages, and the mass of workers working at that particular wage. Okay, so we have these two valuation equations. The first one was the unemployment valuation. So on the right-hand side, we have the instantaneous income and unemployment. Then you've got this contact and offer probability alpha 0. And then what do you get? If there is an offer, you get the integral, the expected value defined over the density df of this valuation improvement for you, leaving unemployment and taking a wage at W prime. Okay, so that's just the classic Bellman equation for unemployment. And then you have the employment at wage W. Now this is taken from an interval from WR, because you could have a really lousy job at WR, or you could be working at the top of the wages distribution, W bar. Okay, so for any of those values, this valuation of employment has to hold. It's a Bellman equation for or a continuation valuation for employment at wage W. So you get the current wage in that instant, and then you get this possibility of getting a raise, okay, or getting a contact with a potential raise. So alpha 1 is the contact probability for employed workers. Doesn't mean you have to accept it. To know whether you accept it, you have to solve that maximization problem inside the integrand, which says if W prime gives me a better valuation of my employment than my current wage W, then I take it. Otherwise, I reject it. That would be 0. And then integrate that over the same wage offer distribution that we had before. Okay, so again, the assumption is we have conditional independence, which means that your offer distribution doesn't change depending on your state. That's really an important assumption. We talked about that last time. Okay, and then of course you could lose your job for exogenous reasons. That's the last part of this expression. So with Poisson arrival rate lambda, you get your job blows up. Your company goes out of business. That's why you want to think about that. So orthogonal to whatever you're doing, whatever your wage is, it's just, the product disappears, can't sell it anymore, you lose employment. So you can see that the value of having a job is more than just the current wage, obviously. That's pretty clear. And then it depends on these two possible events. One is kind of negative, losing your job, and the other is getting a raise and not necessarily losing your old wage. So we have a filter, we're applying a filter to the wage distribution in a sense. If you're lucky enough to get a wage offer with this this probability alpha 1, if it's better, you're going to take it, so you'll end up observing more wages in the better part of the distribution because those are the ones that people hang on to. Otherwise, they say, no, I'll just reject it. Okay, and I'll show you how that looks in a second. Okay, so the strategy to understand how to do this is always you create indifference between unemployment at the reservation wage, because the valuation of having a job is increasing in the wage. Then at WR you're indifferent between taking the job and continuing the search. That's what we've done for the past 4, maybe even 5 weeks. Okay, so that gives us this first equation. So all I've done is basically equate the first Bellman equation with the second, if you like, and then we basically go off and try to solve for WR. That's what we did last time. So we got to this sort of boxed result. But you can see it's not complete because we have the capital W, the valuation, on the right-hand side. We want to eliminate that. That's the whole objective of using this method. And to do that, it's tricky. Before we had an easy go of it. We were able to write, in the old model we had before, we were able to write that simply as a function of the current wage and a severance probability and the interest rate. Remember, it was a very simple expression, and you could just plug it in, factor out lambda plus r, and then it's like an effective discount rate, and we could go to town. We just have to evaluate the integral over the wage distribution. But now we got this W function, and that's a problem. And why is it a problem? Because W is not a trivial function of W anymore. It's not a simple linear function. Why? Well, because we know if you move up the wage distribution, the chances of you getting a job that you're going to take goes down. If you're Bill Gates, you're not going to get anything better than he gets. So the probability of you leaving that job is literally 0. And anything close to Bill Gates will have a very low probability of leaving. So those guys clump there. And that's exactly what this is trying to capture. And the genius of Burdett-Mortensen was to evaluate this integral in this special case, which doesn't reduce like it did before, is you use integration by parts. Okay, so we need to find out, and again, integration by parts says we're going to try to write this integral as using some clever definitions, which I'm going to take you through, is we're going to recall that the integral of u dv is equal to what? Who remembers? Yes. So I mean, this is one of those things you memorize and you put it in your brain somewhere, and hopefully 30 years later you remember it. So I have not forgotten this because it has VDU in it. So if you're an American, you probably have some association with that. If you don't, then that's fine. Okay? You just have to define V and U, and then you define DU and DV, and you just do the substitutions. So that's what we're doing. Okay? And that's really clever. That's why this paper got published. And I want to tell you a little story before I proceed. Mortensen is the famous Dale Mortensen, got the Nobel Prize. Okay? Burdett is his co-author. Not so famous among the uninitiated. He doesn't have a Nobel Prize, but he's a really fantastic economist. Okay? And they basically submitted this paper in 1988. They finished it in 1988. It took 10 years for them to publish it. Okay, so that means that being an academic is hard work, and it's often very frustrating. And this paper is incredibly important. It gets cited all the time. So if you decide to do academics, you're in for the long haul. I mean, and as Professor Sims often said, another Nobel Prize laureate, the good ideas eventually win. It may take some time, but they will eventually win. So take that to heart. Okay, so let's review why we had to do what we had to do. We took this employment valuation equation and we differentiated with respect to W. Remember, capital W is a function of little w, and on the right-hand side you see little w appearing in several places. Everything else is kind of either a constant or it's a dummy variable of integration, that's W prime. So we can differentiate that. If you do that, you get cap W prime on the left-hand side times a constant, the interest rate. On the right-hand side, you get 1, and then you get the arrival rate for a person who has a job, of a wage offer, and then you get this integrand, but you got to differentiate with respect to W. So that's going to be the trick to use the so-called Leibniz rule, which many of you may remember from your Mathe-Leistungskurs. If not, it's easy, but it's something you have to also memorize, like integration by parts. And here we've got basically minus times W prime times the separation probability, chance of a disaster, your job blows up. Okay, so you can look carefully at this and you can see if I can master this guy, if I can evaluate that, then I can actually solve for W prime, and then I can go back and solve the integral for the expression of the reservation wage. And I'm done. Okay? And that's exactly what these guys do in their paper, but they don't tell you how they do it. Right? So we're going to do that. All right. And I do urge you to read that paper. So we've got to evaluate this derivative. So I did that for you. I did this with my other computer, which is completely retarded. It just can't, it doesn't work. I mean, look how bad that looks. I mean, I hate to say this. This is American technology made in China, and the other one is Taiwanese technology made in Taiwan. All right? So this is the derivative on the left-hand side, and there are 3 parts. And that's Leibniz rule. There's a derivative of the function that's being integrated over. That's the integrand. Okay? And you should note that this integration occurs from W to W upper bar. Okay, this constant, we're taking the integration over W prime, so this is a constant, can be factored out. That's the trick. These second 2 parts are the derivatives of the upper and lower bound of the definite integral. So basically, it's the integrand, including df, evaluated at W upper bar. And if you look at that carefully, the derivative of the upper bound of integration is 0 because W upper bar is a constant. So that disappears. So whoopee, we got rid of 1 piece. Okay? The second piece is evaluating the same expression at W, which is the lower bound of integration. So it's W of little w minus W of little w, and that's equal to 0. So whoopee. So now you understand these 2 pieces are equal to 0. So this derivative, making a small change in little w, changes big W only within the integral. Okay, that's the logic. It doesn't change the endpoints. It doesn't change the evaluation of the function at the endpoints. So this is the only thing that survives. And because w prime at w is a constant for this integration, you can factor it out, and then you can just evaluate. Now note WR doesn't appear anywhere in this expression. It's just W. And that makes sense because what this is evaluating is what's the value of having a job. The reservation wage should not matter because you already got the job. Okay? So we had some discussion about that last time. So now you just have to evaluate this piece of mathematics. And you see I've already moved the W prime onto the left-hand side, and that looks like a discounting formula, okay, which it is, okay, right here. And here I just have to evaluate this integral, which is just the density. So it's basically 1 minus cap f evaluated to W. Okay, so again, this is the expression you have in Scheimer, Rogerson, Scheimer, Wright, which they just sort of put as an afterthought, but it's actually not so trivial to derive. Okay, there it is. So you can see that this derivative means that the extra valuation, the extra kick in your valuation of having a job is not only related to the discount rate and the rate of job destruction, but it's also related to the rate of arrival and the possibility of moving up in the distribution. Okay? And because that's a positive number, that's going to make the derivative a little bit lower because, you know, if you're higher up, you're going to have a higher, steeper rate of increase. So I think that's the logic I want to sort of convey on that. It's nice exercise to do that on your own. Okay. I wouldn't ask you to do it on the final exam. Okay, but it's a nice application of Leibniz rule. Leibniz was a German. You should remember that. Father of calculus, one of the fathers, Isaac Newton and Leibniz, all those guys. Okay, so now let's use that result to get the reservation wage down. Okay, so remember the reservation wage formula was WR equals B plus what? Well, the cool thing was we had this race, and I really think you should remember this. This is very useful for your life. Before, the reservation wage was always something positive, but now we've got this race between alpha 0 and alpha 1. Alpha 0 is the arrival rate when you're unemployed. Alpha 1 is the arrival rate when you've already got a job. And the offers are coming from the same distribution. Okay? So if this turns out to be negative, then you might actually have a reservation wage which is lower than your income and unemployment at the present. The integration occurs from the reservation wage, so it's kind of a self-recursive type of result. And it wasn't finished because we had these cap W's hanging around. Okay, and the integration occurs, the dummy variable integration is W prime. Okay, so we're letting W prime run from WR to the top. Okay, so now, this is what we have to evaluate, and I told you already this is a nasty function. It's not trivial like it was before. Make sure you understand why that's the case. It's because of on-the-job search. But Leibniz will help us solve this problem. Leibniz plus integration by parts. Okay, so that's what I want to show you right now. So here's what you do. Okay, first, you're going to, remember it's u dv, v du, remember? Okay, so we have to define u and v. U is going to be w of w prime minus w of w. Remember, cap w is the valuation, little w is the wage at time t, point time t. So what is du? Exactly. dw prime. Remember, w prime is this dummy variable integration, so it's always going to have to show up. If you take a differential of that, it's going to show up, and we want it to show up because it shows up at the end. We do the substitution just like we've been doing all along in this course. So what about v? It's not a very good V. V is going to be f of w prime. And du, or dv, sorry, is going to be df of w prime, or if you like, if you're a stickler, little f of w prime dw prime. It's the same thing, okay? It's just a shorthand. So now I've got the ingredients. Now I just have to go to town and apply the formula. Okay, and then I have to play around a little bit. And it's worth it. It's worth looking at it because it kind of shows you how important doing integration is to this whole. If you ever want to do a paper in this area, it requires quite a bit of, playing with integrals. Because, again, the whole idea behind search is you've got a distribution of wages ex ante. You don't know what you're going to get. And then you have to evaluate values, expected values. Okay, so then we'll take this formula above and rewrite it. So we're going to get WR equals little b plus, as before, alpha 0 minus alpha 1. It's the race between the arrival rates. And then I'm going to use the integration by parts formula. So if you let this be u, then u survives. So we have w prime minus w of little w. And v is now cap f of w prime. And we have to evaluate that at the endpoints of our integration, which are what? W prime equals, I'll write it out, WR, and W prime equals W upper bar. Okay, so that's something we can actually evaluate. And it's going to help us to know that what is f of W upper bar? It's equal to 1, right? That's wonderful. Okay, and we also know that cap f of WR is 0. It's the mass of getting exactly the reservation wage, 0. So that's going to help us a lot. We'll do that in a second. What do we have left? We have minus v du, which is the integral from WR to the top of f w prime. And that's the derivative. Don't get confused. The little w prime is a dummy variable integration. It's a bit unfortunate, but it's also the notation everybody uses. So if you read the original Burdett-Mortensen paper, you have the same issue. Okay, so we just have to evaluate this. Okay, and I'm going to say since f of w upper bar is equal to 1, then we could write w sub r equals b plus alpha 0 minus alpha 1, w of w upper bar. So that's like the jackpot. You get the valuation of the top of the distribution minus w of wr, and then you've got this integral of the rest. Some of our students suffering in the background. It's a great location. Okay, so now we just have to play around with these two expressions and we'll be done. And the trick they do, again, this is something that doesn't get shown, but I'm going to show you, is you want to use a trick which is simply expressing what this thing is. This thing is actually exactly equal to an integral over the same bounds of integration of what? W prime of W prime dW prime. It's the integral of this function, regardless of whatever form it takes, as long as it's integrable, is equal to this expression. And you can see that looks very similar to what we have over here. It's got the similar bounds of integration, so maybe we can put them together. We can put it together, and then we'll be done. Because we have an expression for cap W prime. Remember, that was the whole objective. The reason I tortured you with Leibniz rule is to get cap W prime. Okay. So I'm going to get this minus, and I just, because I'm lazy, I'm just going to copy it like this. Punch it in here. Of course, it's not cooperating. There you go. So what do we see there? We see something that may be useful for us, which is W prime. We already have an expression for it. It's a closed form expression of W, of little w. So if I can just massage this, and remember this is integral. Make sure I don't make a mistake here. This whole thing should be boxed in and multiplied by alpha 0 minus alpha 1. Okay. Now, let's when these machines get hot, they start to act up. It's really kind of nasty. So, right. So alpha 0 minus alpha 1 times W prime of little w prime 1 minus f of W prime. We good with that? And we're integrating from the reservation wage to the top. So all I have to do is substitute for this, except now evaluated at W prime. Let's remind ourselves what we did before. We went back at the very beginning of the lecture, and I tried to argue what I already showed last time. We have this wonderful expression here. Okay, so I need to just substitute that in, reminding ourselves that now we're integrating this function over the interval W, reservation wage WR to the top, and therefore we're going to substitute the dummy variable integration W prime for this expression. Okay, so we're almost there. So we get WR equals B, as it should be, alpha 0 minus alpha 1, the race between the arrival rates, and then we get WR to the top, and then we get 1 minus F of W prime divided by R plus delta. Remember, before we could factor out R plus delta, that was a really cool part about the other reservation wage formula. We can't do that anymore because the other part of the denominator is depending on the wage itself. 1 minus F of W prime dW prime. Okay, so this is an awesome expression. This is the end stage of our reservation wage formula you'll remember to have seen. Okay, so we've got basically it's like pushing up the wage distribution, the reservation wage, because getting your foot in the door. You can imagine if if this should be, by the way, this should be an alpha 1. Excuse me. It should be an alpha 1. So if alpha 1 is equal to 0, then it's useless to have a job in terms of getting better job offers. And therefore, we collapse to the old distribution. We can factor out 1 over 1, 1 over r plus lambda. Okay, so that's kind of proof that we're on the right track. As soon as we have this extra option of getting a raise, it's going to change the reservation wage because there's a value to getting your foot in the door. You get better job offers, better raises, etc. So that means the distribution of observed wages is going to be different from the offer distribution. And that's what we have to remember now. Now we're going to move the logic to the next level. Let me just give you a couple of remarks before we move on. So this is an important formula for us. We will use it later when we derive the observed wage distribution. And again, this is also in Rogers and Scheimer Wright in their 2005 paper. Okay, so let's just think about this for a second. Remember, unemployment in this model is not completely specified yet. We just know that people flow in and people flow out. That's the whole magic of this course. You have inflows and outflows. This model predicts that you will have inflows and outflows at every different point of the wage distribution. You'll have people coming in, and you'll have people coming out. So it's like having a little mini bathtub at every point on the wage distribution. So Mortensen and Burdett actually show that, and they show that if you want to correctly characterize G, you're going to have to characterize what's going on at every point in the distribution. Because if you have a great job, you're not going to be even if you get lots of offers, you're not going to be accepting them. So you're stuck. But if you're at the bottom, just by mere chance, you're climbing this distribution. That's what I said already at the beginning. Okay, so U, if you think about U as the unemployment rate, so that would correspond to assuming 2 states and a labor force equals 1. Okay, so employment plus unemployment equals 1, just by normalization. So du dt is the rate of change of unemployment with respect to time. We use the notation u dot with Thomas, right? So what is that? It's exactly equal to inflows into unemployment minus outflows. This is the same logic that Pissarides gave us in his famous Nobel Prize winning papers in his book. Okay, so it's just it's a bathtub. It's just a big old bathtub, but now the bathtub's more complicated because we have to think about the distribution. Some people are flowing faster and some people are flowing sort of slower. They're all leaving unemployment, employment at the same rate, but they're moving up the distribution at different rates. So this is kind of an interesting implication to think about. So let's write it out very crudely what we expect to see. Inflows we know already. What's the rate of inflow? Excellent. So it's alpha lambda, not alpha, lambda. That's the separation rate. 1 minus u. So think of u as the unemployment rate. 1 minus u is the employment rate, and we're working on a measure of 1. That's the measure of workers, so that's employment. So that's the flow of people into the bathtub. And what's the flow out of the bathtub? That's hard. That's not so hard, actually. We know how to do it. Go back to your notes. Remember, it's an incidence rate, and then it's an acceptance rate. Okay, so you got, sorry. We'll do it your way. U, that's the massive unemployment. I'm just trying to explain to them, all right? And then you've got U times alpha 0. So that's the incidence of an offer, any offer, and then you have to accept it. So it's 1 minus but we know that's just 1 minus f of WR. Because WR is the reservation wage. So if you get an offer that's above reservation wage, you take it. right? That's the whole point of the course. Reservation property. Okay, so basically, and what's a steady state for the unemployment rate? It's du dt equals 0, right? So when that baby is equal to 0, we got a steady state. You just solve for unemployment. Okay, so it's not that hard. It's the same, there's like perennial favorites in this course. They always come back. Every year they blossom again. Here it is again. So it's lambda divided by lambda plus alpha 0, not alpha 1, because alpha 1 only applies to people who already have a job, times 1 minus f of WR. Okay, so that's a really important number. And that, again, it's so important that I'm not even going to say it again because you've already seen it a jillion times. You've seen it. You saw it in Pissarides, you saw it in Mortensen Pissarides, and you saw it recently in the last lecture. So you can see that unemployment is a race between inflows and outflows. Inflows in this model are exclusively generated by this exogenous rate of job destruction, which is lambda, and the behavior of workers in unemployment. Part of it's not their fault. It's the alpha 0, the rate of arrival, and the other is the WR, which they choose because they're optimizing using this reservation wage property. Okay, so if we can affect the reservation wage, think of Hart's reforms, making workers more willing to accept marginal job offers will increase their exit rate and therefore reduce the unemployment rate. Okay, so that's pretty straightforward. It's interesting to speculate how does the addition of job turnover, which is what we have now, on the job mobility, moving up the wage ladder, how does that affect WR? And how does that affect the unemployment rate? It doesn't affect it directly, but it could affect it through WR. In fact, it could raise it or it could reduce it. So this is really test your knowledge. So to answer that question, what do I need to do first? I have to look at the formula for WR. So let's do that. There it is. It's right there. Okay. So what do you see? Okay. You see this guy. And you also see this race between alpha 0 and alpha 1. So if alpha 1 is greater than alpha 0, then it's attractive to take jobs that don't look so great just because I get in the job circus and I can get that next job offer because alpha 1 is higher than alpha 0. On the other hand, you might imagine a world where it's actually, once you're stuck, think of the civil service. In Germany, if you become a civil servant, it's like lockstep after that. So you want to get the right, gehobene Dienst, get an education, all that kind of stuff. If you don't do that, you're in a lockstep that's kind of not so great. So it makes you choosier, and your reservation wage will be higher. Okay, and that means the unemployment rate will be higher. If you have a mass of people who have once they get into the job, that things don't look so great, so they're going to be a little bit choosy. We're going to be careful. So that kind of, it's an indirect effect of this job ladder process indirectly affecting the reservation wage. So this is a really interesting insight that those guys stressed, but it is also known from other authors. Okay, so I should write it down. Alpha 0 and alpha 1 is the big comparison. First off, alpha 1 non-zero changes the nature of the model. It means the accepted wages will look different from the offer distribution because people will tend to reject offers on the job. And secondly, there might be this foot in the door effect, getting your foot in the door. Okay, so alpha 1 greater than alpha 0 would lower WR ceteris paribus, and alpha 1 less than alpha 0 would raise it. Okay, so I love this model. It's a great model. So good. We're going to continue to play with it for another hour. Yeah.
One very short question. But the job offers you get when you're unemployed and when you're in the job, on the job, are the same.
Exactly. Remember we talked about that? I don't know if you came on Friday, but it was called the conditional independence assumption.
Okay, this is conditional.
Yeah. So I'm going to post my notes from last time anyway. So I'm going
I
to.
was there.
Okay. So do you remember that we had that we had made that? I said this is not a subtle assumption because it's basically assuming that you don't get a mark on your head. I'm unemployed. I'm no good, which is a strong assumption. And a lot of people criticize this model because of that. But it doesn't change the underlying logic of the difference between being in and out. It just makes it less grave or consequential or more consequential. Okay, so but that's a good point. We've assumed that they're the same, and that allows us to solve that for the reservation wage. Otherwise, we couldn't do that. Okay, so now let's move. I'm going to take advantage of the last 15 minutes to give you the idea that I think is really important for the rest of the course. Is the idea of GW, which is what we actually see, as opposed to what people get offered, which we cannot see. I mean, I'm assuming we don't have an NSA watching every offer you get. Okay, maybe someday we will. Maybe in some countries they have that already, but theoretically, that's your private information. Okay, so that distribution is not the same thing as this one. And this is the one that has driven our model till now. But what we actually observe is a transform of F. It's a convolution, or it's a function. The reservation wage model implies that the observed acceptances will be a transform of F, even in the simplest case. And remember, this model is so cool because everyone's the same. We all think we know I get better pay because I'm better. I'm better than this guy, or she's better than me, and that's why she's getting paid more. No, it could also, in this model, it's pure luck. It's frictions and pure luck. And that's what makes it so special. And then the idea is, what kind of implications does that acceptance process imply for G? Okay, so to answer that question, we have to answer two additional questions. We have to ask about the flow into the distribution of wages at every point on the distribution. Okay, so again, for those of you who like these pictures, think of this as F. Remember, we have this. Sorry, that's completely wrong. 1, 0. So the question is, what's going to happen to this? This is not what we actually observe. Obviously, anything below the reservation wage will never be observed in the data. If the data generate the model, if the model generates the data, you'll never observe any people working for less than the reservation wage. Okay, so that's a very important insight. And that I'm going to tell you in advance, that implies that the distribution of observed wages stochastically dominates the distribution of offers. Okay, because you can't invent an offer, but you can reject an offer in this model. Okay, so that means that G ultimately will look like this. Okay, so it'll be below and to the right of the offer distribution. And what I would like to do now is to explain how Mortensen and Burdett actually do that, how they map that. So the first task is to show how F generates a G for every point on the distribution. Now G, if you think hard about it, G, if you thought hard about it, you think, well, this must be the case that the induced G distribution has to start at the reservation wage, and that's exactly right. That's the first insight we're going to have. That's robust. Because by construction, there are no idiots out there. They'll never accept a job below the reservation wage. They might accept a job below the unemployment benefit, but they're not going to accept a job below the reservation wage. Okay, so that almost automatically generates something like a stochastic dominance result. Okay, we can show that formally in a second. Okay, so this is neat. So just thinking about what this means means we have to be very careful. Again, our theories have to be very careful. What kind of offers do people get? This model has a very simple theory of offers, but there are lots of different possibilities. So you have lots of degrees of freedom. So here are the questions I want you to answer. Try to answer them right now. One involves, and again, this is like taking every point on G and treating it like a bathtub. Remember? So at every wage, there are people coming in and there are people going out. The going out is easy. That's exogenous. But going in is tricky because it means that people are not coming in unless they were coming from below. Okay, so you're only going to observe people moving up and not people moving down in this model. If they move down, that means they had to have been unemployed for a while and then came back into the wage distribution. Okay, that's the nature of the model. So the first question is, keep it in the same. Ciao. It's one of our guests. Special guest is probably spying on us. Well, I think we're doing a great job today. I think I managed to stay on course and everything. So here's the question. What is the inflow? This is a question. I'm going to write it out. What is the inflow? Underlined. Inflow of workers into jobs paying no more than W. Whenever you say no more than, you think of cumulative distribution, right? Cumulative. It's like F of W is all those W's that are no more than W, right? All those values of the support that are not greater than W, okay? So what is the inflow into jobs paying? Remember, these people could also be coming in from unemployment. They're not just coming in from inside employment. No more than W, and this is for all W that's legit, okay? And we know that you have to have at least the reservation wage, so we're gonna say for all W that come from the interval WR to the top. Question mark. So that is something that we can actually answer using the formal apparatus that we've already played with, right? So again, you can come from outside So what's the answer? Let's try it. Who wants to try it? First off, try alpha 0, that's the incidence for unemployed people. And then we're going to ask, how many unemployed people are there? And then we're going to take the mass of the wage offer distribution between WR and W. Between W and WR, going from above to below. So this is the mass of people who come from unemployment, enter employment, and take a job that pays no more than W. Again, the wage offer distribution is the same. If you get lucky enough to get an offer, it's coming from that wage distribution. Therefore, we always use F. Okay? So F of little w is the cumulative distribution evaluated at W, and F of WR is the cumulative distribution evaluated at the reservation wage. Those are the guys that turned down the offers. So what's left is basically those lucky guys that got an offer that was good enough to get them out of unemployment, but not good enough necessarily to put them over W. Okay, and U star is the steady state now. So go back to your notes and define this one as the steady state, and therefore employment is 1 minus U star, the steady state level of employment. Okay? So let's write this out. This is the incidence of an offer for a unemployed person, an unemployed person. And this is the mass or the volume of workers the mass of the volume of offers between W and WR. I was trying to say WR and W. And this, of course, is the steady state unemployment rate. Now you're asking yourself, what about those guys who got an offer and moved up to W? That doesn't change the mass of workers flowing into jobs paying no more than W. So that's the trick. So if you went from a lousy job to a less lousy job, but you're still under W, you haven't changed the mass of workers that are flowing into the jobs paying less than W. Okay, that's really important for you to understand. So it's kind of a wash, right? Some people, you're moving from one place in the distribution to another one that's still less than W. So you haven't changed the flow of workers, the net flow coming into jobs. Okay, you get that? What matters is people coming from outside employment. Okay, that won't be the case when we talk about losing jobs. So I'll finish this and I'll repeat it for you, okay? Because this is key, but I do believe that Scheimer, Rogers and Scheimer, right? This is a great advertisement for those guys. In this paper, they do go into some detail. And you can also read the Burdett-Mortensen paper. It's very difficult, though. Okay. All right, so that's kind of neat. That's going to help us. That's question 1. Question 2. Question 2 is, what is the outflow of workers making W or less? So when I say W or less, bing, you think of cumulative distribution function. Okay? So I'm going to use the same logic to write down that expression, and then we'll call it a day. So 2 is, what is the outflow and by this is also inflow of workers into jobs. Maybe that's one reason why it may be unclear. Workers into jobs paying no more than, i.e. less than or equal to, W, and W, of course, comes from that same interval. Okay, so this is like winners and losers, right? This is the guys that are leaving. And that doesn't mean they're losing, because they might actually get a promotion. So that's going to make this a little bit more interesting. Okay, so we have to ask, why do you leave a job paying W? One reason you leave a job paying W is you got laid off, and that occurs with lambda exogenous probability. Okay, who wants to try the rest? So if you're making less than W, why would you leave that state? Out of jobs, yeah. Thanks. Get too excited. It's kind of a different concept, isn't it? Sorry about that. All right, so again, bathtub at each point. Everybody understand? Think of the bathtub at each point in the distribution, or at each chunk of the distribution, if you like. For every W, we're kind of setting up a bathtub for every point W. Everything that's happening below W, you have exits and entrances, or inflows and outflows. And the outflows are what? So I told you already. Well, actually, why don't we go start at the very beginning? What is the mass of workers at risk? Yeah, 1 minus U star, that's part of it, but not everything. That would give you all the workers that have jobs. But now we want to ask, sorry? Alpha 1 does matter, yes, okay, but let's go slowly. Let's talk about the mass of workers first. So the mass of workers who are earning no more than W. So I'll give you a hint. This does not involve F, because that's the distribution of offers. We're asking about the workers who got a job. So you're looking at the other distribution. We called it G. Okay, so that's the key thing to think about, and that's what makes us able to solve for this distribution, because we're going to put those two together, and then we're going to solve for the function that sets these two inflows to outflows for every point on the distribution. Okay, so we're not done yet. That's the mass of workers at risk, and when I say at risk, I mean it could be positive. You can move up the ladder. You can move down the ladder by losing your job, but you're never going to accept a job that pays less than what you have already. That's the model. You're putting a filter on all the job offers that are lousy, and just ignore them. Right? It's like a spam filter. So, lambda, those are the people who have bad luck. So they lost their job and they go into unemployment, and they have to start from scratch. Okay, and then you correctly said alpha 1, that's the probability of getting an offer on the job. And then, again, it's an offer, maybe a lousy offer. And given that we're looking at all the stuff that's happening below W, what is the chance of getting an offer that's above W? What is the probability of getting an offer above W? It involves F, because it's the offer distribution. It's 1 minus F of W. That's the probability of getting any offer that's better than W. So it's 1 minus F of W. So that kind of nasty looking thing, actually it's not nasty, it's quite beautiful. You can see it depends on a lot of stuff. It depends on the exogenous incident rate of job destruction or worker match destruction, you can call it in this model, because workers and jobs are kind of synonymous. Firms just, they don't hold the job and try to get a better worker. It's just, that's a different model. Okay, so you see now that we've got two objects, two objects. And I don't think I'm going to write down I already told you what they are, but again, it's the exogenous part, and then you've got this part that depends on where you are on the distribution. And obviously, if you're at the high up in the distribution, the number of acceptable offers that will make you move even further up gets lower. Right? Think about it. If you have Bill Gates' wage, then W equals W upper bar, and then F is equal to 1. 1 minus 1 is equal to 0. So that whole thing disappears. Yeah.
So then, are we looking at a certain point at the distribution, or
no? We're looking at inflows and outflows. Maybe I misspoke, or I spoke a little bit loosely. It's inflows and outflows for all of the mass of the distribution below an arbitrary W.
Okay. Because in the outflows, we looked at zone who changed the job, so which get a better offer.
Right.
If I'm not mistaken. But in the inflows, we don't.
And the reason I tried to tell you, maybe I wasn't clear, is that The only thing that matters for the mass below W are the people that come from unemployment, because if you move within the distribution below W, you don't change anything. You're moving, of course, but you haven't changed the mass of workers paid less than or equal to W. Okay, so there's going to be people moving, and this is a functional equality we're going to impose across for all values of W. So we will capture all things you're worried about, because at the very low end of W, we'll have some turnover, but it has to exactly match the outflow at that low wage. It has to hold for all wages. So it's a functional equation. It's an equation that holds for two functions, and that will allow us basically to express one function as the other. So in the end, what I would like to do next time, because I'm running out of time, is to express G as a function of W. It's a function of the function W. And then, of course, you're going to have to ask the question, well, that's not enough. We have one equation and two unknown functions. So we're going to ask what kind of policy of firms would lead to an offer distribution that is compatible with this model. And that is Burdett-Mortensen. That's a complete characterization of Burdett-Mortensen. Okay? So let me just wrap up. Did you get that?
Yeah.
Think about the bathtub, and maybe I spoke a little bit too glibly. It's actually, the bathtub is every chunk of the CDF. Okay, so think of this beautiful thing. For any arbitrary value of W, everything that's below that is like a little bathtub. So that's a bathtub, that's a bathtub. And I'm making sure that for every value of W, this bathtub identity, steady state, holds. That's going to force those functions to behave in a certain way that's consistent across the entire distribution of wages.
Yeah.
Okay? So I'm sorry if I spoke a little bit too glibly before, but that's what I wanted to say. It is a nice way of thinking about it, because bathtubs actually don't work for a point, they work for some positive mass. So it does actually make more sense to say it that way. So my next Monday, I'm going to make these two guys equal. I'm going to set these two expressions equal to each other. And you see that it has to be true for every W, not because little w is the function. So we're going to solve, and that again, you just look at it, you can see, looks like I have a chance of solving for G. It's not always the case. So you may have to do it numerically. This is actually algebraically in this model. So we have G, and then we can use that as a springboard for having a theory of F. And that's why that paper took so long to get published. It's really hard. It's a hard paper. Okay, but I think if you invest a little time in it, you'll understand why it's so interesting. It's going to give us kind of a baseline rationalization of unequal wages for identical people, which arises just because of some friction, just because it takes time to get to the next job. There's some barrier you have to apply, whatever. These exogenous arrival rates also have some micro foundation in the background. Okay, that was a lot of fun, but we're not done yet. So if you have a chance, read this paper and look at the notes, and I'll try to post these as soon as possible, okay? Good. See you.